good. Okay, picking up where we left off last time. So we had just finished section 5.5, the gigantic monster of a section. Finally made our way through it. 5.6 is another, just kind of a quickie. And there's applications in here. It's mostly applications. Tough choices and all that. I'm going to go a little bit quickly through this. Here we go. Let's talk about the average value of a function. We're going to start with just the idea of averaging numbers, and I think you all know how to average numbers. Here I'm averaging 6 numbers. But kind of I'm only averaging 3 numbers. Right? Sort of. A little bit. I mean, it's 4, 7, and 8 are the numbers I'm averaging. Right? But I'm averaging 4 twice. Like it counts twice. We're double counting the 4. And now, if you look at the sort of arithmetic equation that follows, and there's no tricky curves in that arithmetic, right? But you notice that 2 kind of shows up like so. And then likewise, we are sort of including 8 3 times. And again, you see how that 3 sort of shows up here. Right? So this is called a weighted average. You can view this trivial arithmetic as either a straight average of 6 numbers, some of which happen to be the same, or you can view this as what we call, again, a weighted average of 3 numbers, 4, 7, and 8. All right. You will notice that this formula for a weighted average, this generalizes pretty easily. Yeah, you write it down as this formula right here. And these numbers that were, how many times did we count which numbers that were being multiple counted? Those show up there and there. These are what we call the weights. It's just a way of saying kind of how many times more than other numbers are we counting them. And then you notice that since we're no longer writing this as explicit average of finite number of numbers, we've got this as a formula. There's now no particular reason that the weights have to be integers. Right? So you can make the weights whatever you want. And it's kind of a continuous version of our motivating example here. So a nice example of that, this idea of a non-integer weighted average, is how we do grades in this course. Right? So y'all, I hope, recall that we have a explicit formula for how grades are computed in the course. Part of it's on the course website and part of it's on the class website. Right? Okay. And the big idea is it's literally a weighted average of the various grades that you get on the 4-point scale. A equals 4, B equals 3, like that. And various weights are advertised. Now, just to keep the arithmetic convenient, I'm going to use these relatively convenient numbers as the weights, but whatever. It doesn't matter, right? In our actual class, something is worth 7% and something's worth 3%. It just makes the numbers weirder. But same basic idea. And notice certain grades that Bob earned, right? These are the things that I'm averaging. And then we have these weights right here. And the weights go where the weights go, and plug and chug, right? Nothing to it. And you can compute that Bob's course average is that. And pretty close to 3, right? So Bob gets a B. Does that make sense to everybody? And by the way, I hope this is possibly helpful to y'all in understanding, making sure you have a crisp understanding of what the grading system is for the course. And if you're still not entirely sure, something you may be a little confused about, come talk to me, right? It's very important for everyone to understand the grading system. I'm happy to elaborate, whoever would like. If it's something about the way it's written on the website, maybe you don't quite, not sure how to interpret. Whatever. Let's talk. Come talk to me. Okay, so here's kind of a generalization of that idea. I'm going to try to get this all onto the screen at the same time. Sort of another generalization, right? Here, this original formula, we were talking about a finite number of numbers, right? And therefore, we're going to have finite weights. We can generalize that, though, to talking about the average value of a function. A function takes on infinitely many values over an interval. There's infinitely many inputs in the domain, and therefore infinitely many outputs that come out. And how do you average infinitely many numbers? This is kind of a continuous rip-off, really, of that formula. I hope that looks kind of believable. And the one little subtlety is we use size in the domain as the weights. And you see dx, right? How, size in the domain, literally, playing the role of the weights. Okay. There are different ways to motivate this formula, and you may have seen some of these in high school. Some people like to draw a picture and argue that the average value of a function is the value where if you make a rectangle, then the area under the graph is the same as the area of the rectangle. And it is a perfectly reasonable take, and that's what we're thinking through. I like this one better. It's because we are generalizing something that we're calling it. Right? I think that's a nice connection. Okay, same deal for functions of two variables, or any number of variables really, but here you see we have a function of two variables, and again I just use size in the domain as the weights. And now double integrals because we have a function that's defined on a two-dimensional domain. Alright, how are we doing? Let me pause here real quick. Is everybody willing to buy? It seems like a reasonable extension of just weighted average. Okay, here's another cool sort of extension. Now that we have this idea of weighted average of a function, let's talk about this thing called center of mass. There's various different ways to define center of mass, and by the way, the applications we're going to be doing in this section are pretty engineering-y, physics-y kind of stuff. So different ways to talk about center of mass. This one's actually pretty cool. It is a weighted average of position. Nice and simple, right? It rolls off the tongue very crisply. So notice that's what we have here, right? The center of mass is the weighted average, and you can see the weights. I'm literally using the masses as the weights. And we're taking a weighted average of their positions. Where are those masses located? Weighted average of position, literally. And if you compute where that is, right, and if you were to imagine that this is some sort of single rigid thing, nice physical interpretation is that the center of mass, that's where you put your finger to balance the thing. Whatever this thing is that has a certain amount of mass over there and a certain amount of mass over here. This is what makes it balance perfectly, or you might say that the total torque is zero. In other words, the sort of counterclockwise torque that M1 is sort of doing and the clockwise torque that M2 is creating, they balance each other perfectly. Oh, yeah, kind of a cool concept. So we can generalize that to continuous distribution of mass, so we might as well just jump right to doing so in a vector fashion. And here you go, weighted average, right, let's see here, let me not get ahead of myself. Weighted average, using the mass as the weights, weighted average of position. And of course, position is defined by a location vector, which I'm calling X vector, because I don't want to deal with the different letters X, Y, Z. I want to be able to write down as many coordinates as I want. So this X vector is X1, X2, X3, etc. And again, you can streamline the formula like so. Now, what's weird about this formula, if you look at that expression, there is something new and kind of unique about this formula. This is the first time that we've written down an integral where the integrand is in fact a vector. I think this is our first time to do that. Oh my gosh, what do we do about that? Are you even allowed to do that? A lot of reasonable questions come up. And the short answer is, yeah, totally fine. Let's break this down one little bit at a time. I have a vector here. Okay, how do I multiply a vector times a scalar? One coordinate at a time. Okay, so natural. to do so. All right. Now, this is a vector. How do I add up a bunch of vectors? One coordinate at a time. Right? So, hopefully not a difficult pitch if we interpret x, again, as a vector with coordinates x1 through xn, then this integral, you just compute its coordinates, one coordinate at a time. How we doing? Yeah.
So the result is also a vector?
Also a vector. That's right. Which, if you think about it, it really should be. I mean, the reason we have a vector in here is because x vector represents position, right? And if you think further about it, okay, well, what should the center of mass be? It's also a position. So yeah, really, so it should be a vector, and yes, it definitely is. Okay. Alrighty, let's do one. Here is, let's see here, we have the upper half disc. Oh, circle the whole thing. This upper half disc here. Now, just to get the ball rolling, nice, easy first example, we're going to say the mass is distributed across that upper half disc with density 1. Right now, in general, doesn't have to be in general. Density could even be a function. It could vary over position. But let's just keep it convenient. Density is 1. Plug it into the formula then. If I want to know the x-coordinate of the center of mass, there's the integral I have to compute. And I'm going to leave this as an exercise. It's a nice little exercise for y'all to think about. And by the way, this is how stuff shows up in, when I said 20% of the integrals that I had to deal with as a undergrad physics major, integral zero by symmetry, right? It comes up like this, unannounced. Here's an integral that naturally makes sense for physics reasons, and if I just have the blinders on, plug and chug, I wouldn't necessarily notice, right? But when you draw the domain, you realize, oh my gosh, look at that, there's an axis of symmetry there. How does a reflection behave? Is my integrand odd? By way of that reflection, oh my gosh, everything works. This integral is zero by symmetry. And I just encourage you all to think through all those details, make sure you're quite comfortable with why that works. And we just saved ourselves a bunch of effort. Everybody happy with that? Okay. So again, keep your eyes open for that. It happens a lot. It's well worth constant head on a swivel. Okay, now let's look for the y-coordinate of the center of mass. Again, formula. And now here's potentially a landmine. Right? This is one of the kinds of things that you have to also be on the lookout for, because you might think, again, oh my gosh, look at my domain. My domain is clearly symmetric. Oh my gosh, look at my integrand. My integrand is an odd power. Makes it feel like it's going to be an odd function, but it's not. Right? It's only, that y would only be odd if we were reflecting over the x-axis. Over the y-axis, y doesn't change at all. This is not an odd function. How we doing? Everybody happy with that? By the way, we can also, if you're just wondering, strategically, how can I defend myself against these kinds of things? How can I sort of watch out for landmines? Well, just from the picture, you can kind of tell the center of mass is it's gonna be something in that general vicinity there, right? And now, eyeball glance, I'm very willing to believe that the x-coordinate is 0, and I am not even remotely willing to believe that the y-coordinate is 0. Right? So let your physics intuition help you out sometimes. So that'll defend you against this landmine. Okay. Now, I also like to throw out here, and this is just a kind of a computational strategy thing. This integral, I can write it as an iterated integral in either of two different ways. It's a question of how I do the differentials. So which one is better? They both have square roots in the bounds. Don't be don't be drawn in by the idea that this one has twice as many square roots. It's not really the point. The point is both of these outside integrands, right, are under threat of having square roots in them. That's really the point. So, okay, what about corners? You know, when we slice this way or when we slice that way, do we slice through any corners? No, not really, right? Both of these have square roots in the bounds. Both of these, you know, miss all the corners. You would think that these integrals are equally convenient, and they're definitely not. One of these is highly more convenient than the other. And so now, how often does stuff like this come up? I can't quantify that. It comes up often enough that it's worth kind of, again, keeping your eyes open. Sometimes the very first thing that you do in the evaluation will help you deal with your ugly square root bound. And you see here the very first thing that I do is I take a y antiderivative. This turns into y squared, and this square root gets plugged into a square. And the square roots go away, and it's all downhill from there. Everybody see that happening? So, you know, how often is this the criterion by which you should make the decision? Well, I don't know. It's a little harder to see coming sometimes, but it's definitely, you want to keep this on your list of strategies to be thinking about. Okay. Moving along. So we got this thing called moment of inertia. It is a physics idea. It's an important physics idea. It's also an important engineering idea. And I'll say a couple of quickie things about that once we have it more developed. The big idea, the starting idea, I'll say, is that if you have some axis and if you have some particle that's moving around it, we want to ask the question, how much kinetic energy does that particle have as it moves around? And now y'all know the formula for kinetic energy. The formula for kinetic energy is, here it is. 1/2 mv squared, right? So boring, no problem. You might have to do a little work to figure out what the velocity is, but it's cool. Okay, here's where it gets weird. Let's suppose that my solid is not a single point. Let's suppose that my solid is a lumpy thing, like so. This is the mass that's rotating around that same axis. Great big lump like this. Can I use this formula, 1/2 mv squared? And I say not really, because different pieces of this mass are going at different speeds. This little piece of mass right there is moving at one speed, and this little piece of mass here, well, this little piece of mass on the outside, as we rotate around, it's going around a much bigger circle in the same amount of time. It's literally going a faster speed by quite a bit. So 1/2 mv squared, what do I use for speed? Different parts of this are going at different speeds. That's a problem. Everybody kind of see what's going on there? There's an issue. So how to deal with this? Turns out there's a nice answer. And let's see here. I think this will be good enough. I wish we had time to go through this development, the tough choices. And this, you're not going to be tested on this stuff in this class. And so, oh well. By the way, if you're curious, if you're any physics majors or anyone who wants to understand, wait, how did we get through that? Come talk to me in office hours. I'd love to talk about this. It's actually pretty cool stuff. Anyway, the punchline is that the kinetic energy that we can't compute with this formula, velocity is not the same. We can instead compute with this formula. And you look at that formula and you think, so that's pretty inconvenient. It's pretty unnatural looking formula until you notice that this thing here doesn't directly have anything to do with the motion. This is just an integral over your domain. You need to know the mass. You need to know how far each piece is away from the axis. But this doesn't have anything to do with how fast is it going. This here is intrinsic to the mass itself. Right? And so what we do is a clever move. We give it a name. We're going to call it moment of inertia. Give it that name. And now let's compare. Let's see here. Oh gosh. Okay, here we go. Let's compare this formula to that formula, both computing kinetic energy. Difference being that this original formula is about how would we compute kinetic energy of a particle that's moving linearly, right? And this came to us by thinking about how would we compute kinetic energy if the particle is rotating, not moving linearly, right? And first thing you notice is, oh my gosh, it's 1/2 something times something squared. It's structurally, it's kind of, that's an eyebrow raiser, right? It's kind of convenient. And then you notice that this is what we call angular speed, is playing the role analogous to regular speed, right? So V is regular speed, and I'm going to phrase this in a way that I think is helpful. This is the change in linear position per unit time. This angular speed is the change in angular position per unit time. Right? So this is really very analogous to the linear idea of speed. This is just an angular analog. And then you think to yourself, oh my gosh, well look, these formulas are really similar structure, and as far as the motion goes, we've got this angular versus linear analog, and the reasonable conclusion then is that this thing is kind of an angular analog of mass. I think it's a really nice take. This, to me, is very helpful for intuition from the point of view of kinetic energy. Moment of inertia. This thing, computed by that formula, referred to by that name. This is the way to think about it. It plays a role analogous to mass when you're thinking about rotational kinetic energy. All right, now that's physics. This is not a physics class, but I hope that might be helpful when you use this in your engineering futures. Now let's come back up here real quick. Notice that our mass, right, going around an axis, and I referred to this distance, and let me do it like this. It's the distance from the thing, whatever little piece of mass I'm interested in, how far is that away from my axis of rotation? I called it R, and I did that for sort of, that's what everyone calls it, right? And awkwardly, though, it's not the same R that we've talked about previously. It's not the cylindrical coordinates or polar coordinates R. And just to emphasize this, you notice I deliberately made this axis tilted. This is not necessarily the z-axis. It's usually not the z-axis, right? So, it's frustrating when this happens, but the notation that we have to work with is a little misleading, and sadly, we just have to remember to defend ourselves against that. So, R is the distance from whatever little piece of mass you're looking at to whatever your axis of rotation is. Keep that in mind. So a couple of quickie examples. Let's suppose you have a mass that's rotating around, let's say, the z-axis. What if it's the z-axis? Well, then, yeah, that's good old cylindrical R. But if your mass is rotating around that axis, what we're calling R here, the distance from some little piece of mass to that distance, well, it's not the cylindrical R. You can see right there in the picture. I mean, the little geometry, right? Nothing particularly heavy about this geometry. It's just not the cylindrical R. Now, how do you deal with it? By the way, a couple of different equivalent conceptually equivalent examples. These are kind of two-dimensional masses, and again, it's always distance to your axis of rotation. How do you deal with this in practice? One approach that I do not recommend is to memorize a finite list of cases. Well, the axis is either going to be x-axis, y-axis, z-axis, or maybe various different lines parallel to those axes, a finite list, right? And then just, go off of those formulas. And there's two problems with that. First of all, I don't believe that you're going to be able to remember those your entire life, right? It's just, you're going to forget, right? You might be able to remember them in time for the test. 10 years is a very, very, very long time, and I don't think you're going to remember, right? And second of all, it blurs the concept, right? There is a point. There is a single geometric concept that you can remember, that you should remember, that can feasibly stay with you for your entire professional career, which is that, well, this is what R is supposed to be. It's the distance from whatever little piece of mass you're looking at to whatever your axis is, and that little geometric concept will allow you to solve every future such question. So here's an example. Suppose we want to compute the moment of inertia of a certain mass, and here are the particulars. The mass is distributed over this region. Let me do it like this. Mass is distributed over that region. The density, you'll note, not constant. Right? 2 plus cosine x, that depends on x. It's like it's more dense sort of around here and more dense sort of around there and less dense in the middle. And we want to find the moment of inertia, it says here, around the x-axis. So there's our axis. Okay, so how do we compute the moment of inertia? Well, we play the usual game. Let me clean up my mess. Play the usual game. You'll notice that we're doing a double integral over the given region. And you can see the dm happening. Mass is density times area. And you'll notice that that's all this is, right? We have the given density times dA being, of course, dy dx or dx dy, take your pick. And here's where we have to actually kind of think about, okay, hey, what's going on here? How does this actually work? And in particular, if I look at a particular little piece of mass, here's some little particular piece of mass on my region, and let's see, my axis, it says, is the x-axis, so there's my axis. Now, just like these examples up here, I'm going to understand R as being the distance to the axis, the stated axis of rotation. And that distance here is y. Right there you go. I mean, it's right there in the picture, right? So y is what R is, and so this R is y. Everybody see what happened? It's pretty plug and chug, except for the fact that I did have to make this interpretation of, wait a minute, how do I interpret R in this and notice, not square root of x squared plus y squared. That would just be way wrong. Yes?
The little 4-inch mass
isn't
on the y graph. It's in the shaded gray area.
Yeah. Well, that's right. So, I'm sorry, I interrupted. Go ahead.
So how would R be y?
Right. So this doesn't say y equals sine x. It says y is less than or equal to sine x. Right. So that includes all of this stuff. Does that make sense? Yeah. So this particular little piece, when we do integrals, a generic piece that we're talking about, that's x comma y, and so that distance is y. Is that satisfying?
Yes.
Cool. Okay. Last little quickie thought. Make sure you still remember how to do these kinds of integrals. You see, I just wrote ... right? That is single variable calculus at this point. And it's, one of these integrals is a little bit tricky. You gotta remember the move. In particular, this times 2. Gotta remember there's a little slick, little clever move how to do that. And I am sorry to report that kind of little annoyance doesn't go away. It will be with you for as long as you're doing anything analytical that requires calculus, which is most of engineering, right? So make sure you can still remember how to do this kind of thing. A reminder, I think I mentioned this before, we, the math department, we have been specifically and emphatically requested by Pratt to make sure that y'all maintain your integration skills. So I'm sorry, but it is important. You got to remember, maintain your polish on being able to do that kind of thing. And as always, if you have any trouble with anything in particular, come to office hours. Happy to help. Okay, so that's chapter 5. On to chapter 6. Very exciting moment. This is where things start to get kind of wild. There's some really, really interesting, important ideas that come up in chapter 6 that we're going to sort of extend in chapter 7. Let's just do it. You may or may not have noticed this. This is an important observation. We've talked about single variable calculus. Integrals on intervals on the x-axis. The interval, one-dimensional. The x-axis, one-dimensional. We've talked about double integrals over regions in the plane. The region, two-dimensional. The plane, two-dimensional. Likewise for three-dimensional. So every kind of integral we've ever looked at has been, I'm going to say, dimensionally sort of convenient. Right? We're going to address this nasty little question here. What if that doesn't happen? Right? What if, for example, what if I have a curve? Here's a curve. And that's going to naturally be a domain for I feel like it ought to be an integral, but the problem is that's a curve in the plane here. Right? That's two-dimensional. Or same question comes up if it's a curve in 3 dimensions. What kind of an integral that we hopefully, fingers crossed, we hope we might have seen already, what kind of an integral would I use for this? Well, it's not going to be a double integral, right? I mean, this is a two-dimensional question. This domain, very importantly, not a straight line segment. This lives and moves in 2 dimensions. Right? So you might think double integral. The problem is there's no area on my curve. My curve is a one-dimensional curve. There's what area? What would be dA? What's the range of values of y? It doesn't make any sense. And then likewise, if I say single variable integral, I go, you mean Calc 1? When in Calc 1 did you see a domain that was curvy like this, right? So we have a problem. This is not the kind of thing we have previously seen. So we're going to resolve that matter. The notation's a little bit inconvenient, so I'm just going to streamline the notation. Structurally, strategically, we're going to steal all our old ideas about integrals. In the same way that we said, look, double integrals, morally equivalent to single variable integrals in the sense that we break up our domain into little pieces. On each little piece, we multiply size of the piece times something for whatever reason, appropriate to the application. And then we sort of add up over the domain, whatever the domain might be. That's all we're going to do here. Here's our domain. You can see I'm literally breaking it up into little pieces. On that piece, on each individual little piece, I'm going to multiply the size of that piece. Okay, quick pause. Let's go to our picture. What do we mean by size of the piece? Well, this little piece of curve, this is a little one-dimensional length. Right? Size on a curve means length. So delta x. And we're going to multiply that by something for whatever reason appropriate to the application. And remember, there's different ways to think about your integrand. My favorite way to think about integrands is that they're densities. It's some sort of a quantity per unit size. And if we're computing mass, then this would be mass per unit length. If we're computing population, maybe this is a wire that has bacteria growing along the wire. If I want population, then it's population per unit length. Whatever it needs to be, the appropriate density appropriate to the application. So that tells me how much of the quantity that I'm interested in is happening on each little piece, and then you just add up over all the pieces. So this formula here, here we go, this Riemann sum, right? Structurally and strategically, it's a shameless rip-off of single variable integrals, double integrals, triple integrals, any kind of integrals, whatever. Chop it up into little pieces, add up over all the pieces. Is that cool? I mean, many questions remain. How would we compute such a thing? And what sort of examples would this apply to? Yeah, lots to talk about, right? But strategically, this seems reasonable. Yes?
Let's say that this line was a line of population.
Mm-hmm.
What would that final answer Q represent?
Total population. Like if we're counting bacteria, right? So like if this is, medical device, right? And we've inserted I forget the name. I don't know anything about medical anything, but they stick wires inside of people that go through their veins and get to their heart or whatever. And if you're trying to keep track of how many bacteria are growing on that wire, right? Then Q would be the total amount of bacteria. And then F would be how many bacteria per millimeter, or how many bacteria per centimeter, or whatever. Is that satisfying? All right. And here's our notation. I think the notation's pretty believable. You see that we just use differentials as a shorthand for size, and we recopy what the F is, and a limit of a sum is an integral. So now it's just notation. This is just so we can have a shorthand, so we don't have to write all of this down with all the little subscripts all the time. Just notation, right? I think it's a pretty reasonable notation. So this is called a line integral. And by the way, real quick, we're going to specifically call this a scalar line integral because you'll notice our integrand is a scalar. And now the following I'm going to say is going to sound pretty weird, but also the differential is a scalar. Well, of course the differential is a scalar. What, is there a vector differential out there? We've never seen or heard of such a thing, right? Guess what? It's coming. We're going to talk about integrals where the differentials are vectors coming up pretty soon, possibly today, kind of betting against, but certainly very soon. Anyway, for this integral, integrand and differential, both scalars, so we use the term scalar line integral. Okay. All right, how do we compute these things? I'm going to say the problem is that our domain is weird. I don't like the domain. We've seen undesirable domains previously. When we were doing change of variables, what was undesirable is that our domain had corners in inconvenient places, or the equations were awkward to deal with, and the idea of pulling back to a better domain was to deal with those problems. Here, what makes this domain undesirable, there's this additional concern that this is dimensionally weird. It's a one-dimensional thing in a two-dimensional world, and we don't know how to deal with that, right? So, that said, we're going to deal with an undesirable domain the same way we always have, which is we're going to find a way to view that domain as being an image, and then we're going to pull back to a new, more desirable, in this case, just an interval on the t-axis, more desirable domain. And good news, we already know how to do that. The function, parameterization, right? Goes way back to chapter 1, right? And at the time, when we were in chapter 1, I was saying this can be really important in chapter 6, chapter 7. And here we are. We parameterize this curve so that I can view it as an image and so that I can then talk about a pullback. And if you think about it, this creepy, spooky concept of doing an integral on a curve that's moving in 2 or maybe 3 dimensions, it seems totally weird. How do I deal with that? Once I pull it back, single variable integral, t-axis, calc 1. Good old-fashioned integral. All right. Okay, so here's what that looks like. The big trick is understanding the stretching factor. In particular, if I have a little piece of the t-axis, it's going to have an image that's a little piece of my domain, little piece of my curve. And, well, let's think about this. This dt represents, think of t as being time, very convenient. Thinking of t as being time, this represents some sort of a small amount of time. And this, again, thinking of t as being time, this represents how far my position changes over that amount of time. Displacement per unit time is speed. Right? So our stretching factor, the thing that we multiply by dt to get ds, is speed, aka the magnitude of the velocity vector, aka the magnitude of the derivative of the parameterization. And don't forget to insert that stretching factor into your integral. How are we doing? Does that seem kind of plausible? Alrighty, so before we get to an example, I had just one little sort of worry that I want to address and then subsequently ignore conveniently. Hey, wait a minute. This thing that I'm trying to compute, this integral representing the total mass of the wire or the total number of bacteria, climbing around on my medical device, whatever this might be representing, this formula that I've proposed for how to compute it seems to depend on my parameterization, right? So wait a minute. If I parameterize one way, if you parameterize a different way, are we supposed to be getting different answers here? We seem to be, but certainly we're computing different integrals. How do I know these integrals aren't going to give me different answers? And if I get different answers, that's a problem because the answer we're looking for should be independent of arbitrary choices about how we parameterize. And the good news is, yep, it is in fact independent of the parameterization. Believe it or not, how you stick, what R you put in there to parameterize your curve, do whatever is most convenient for you because you'll get the same answer either way. Is that cool? So thankfully, not our problem. Okay. Alrighty, so let's do one. Actually, we're going to do 4 of them. Kind of all at once. Here's the problem. We have a weird irregular wire. It's thicker in some places and thinner in some places. Maybe it has more iron in the alloy part of it and has more aluminum in the alloy elsewhere, whatever. So it's just a non-constant density. And it follows a certain curve, and I'm going to give that curve pre-parameterized. By the way, you could probably recognize that curve. That's just y equals x squared, isn't it? Anyway, pre-parameterized. we're looking from where t is 1, and then all the way up to where, sorry, I said that backwards, starting where t is 0 and ending where t is 1. So this is our parameterization. And here's, when I say that it's an irregular wire, irregular in the sense that the density varies, and in some places the density is higher, some places the density is lower. And the question is to compute actually several things. On the one hand, I would like to know total mass of that wire. I would also like to know, hey, where is the center of mass of that wire? And while we're at it, maybe I want to know what's the moment of inertia around the x-axis. Is that cool? We're going to try to do all these calculations. Big first observation is that all of these questions are about the same wire, which follows the same curve, which is parameterized with the same formula, which therefore has the same derivative, which therefore has the same speed and therefore the same stretching factor. So really nice that even though we're computing a bunch of different things, right, this is arguably 4 separate calculations because the center of mass has 2 separate coordinates, right? All 4 of these calculations, they're all going to use the same parameterization and the same stretching factor, and all that's the same. So there's going to be a lot of reproduction here. In fact, there's going to be so much reproduction, I'm really only going to do, I'm only going to write out the details anyway for 2 of these. So let's start with the mass. Now again, I like to doff the cap to mass being an accumulating quantity. The whole is the sum of the parts. Right? That's a little superstition of mine. I think it's nice to recognize that. We already know, by the way, that mass is mass per unit length times length. By the way, the mass per unit length was given. Right? We argued on the previous page. We argued on the previous page that R prime is our stretching, magnitude of R prime is our stretching factor. So stick that in there. We've already computed. Give me 2 seconds. We've already computed that magnitude of R prime there. And one last little tricky bit. Wait a minute. What do I do with X here? It's really easy to lose track of this. Remember with change of variables, the way I pull back, the change of variables function is literally telling you how to pull back. Here, same story, it is the parameterization that's telling you how to pull back. Right, so X is literally T, and likewise Y, there it is, Y is T squared. Yeah, there was a hand, yes.
Wait, how do you know that dm is equal to the symbol?
Yeah. So the idea of a density is always stuff per unit size. The stuff depends on it depends on the application. If you're talking about mass density, then it's mass. If you're talking about population density, then it's population. Whatever the nature of the stuff is, and it's stuff per unit size, with size appropriate to the context, right? So here we're talking about mass being distributed over a curve. The notion of size on a curve is length. So the notion of density in this context is that it's mass per unit length, or said differently, it's what you multiply by length to get mass. Okay. Is that satisfying? Cool. Everybody happy with that? Okay, now let's talk about the x-coordinate of the center of mass, and this is awesome. Check this out. All of that comes up again over here, all of that same stuff. Right? Here, just right, here's our old formula for the x-coordinate of the center of mass, and there's that dm. dm is going to play out exactly the same way that it did in the last example. And the only difference here is, well, there is, I do have this 1 over m that tags along, and yeah, okay, we are computing that m over on the, okay, fine, that's annoying, but it's there. And then this x, this extra x, well, don't forget, there it is. X is just t. So, pretty much the same development. We adjust the integral appropriate to what we're computing. Most of it's the same argument. How we doing? Everybody happy? Okay. Be good for you all to check out these other two arguments. They're very, very analogous, and this is a pretty good place to draw the line. We will pick up here on Wednesday. Y'all have a good rest of your Monday.
What? The content on the